Alright, so let's start again here. Lecture 2, I suppose, on cross products. I'll start with cross products, see what we get to. So I have, tell you what, let me cover up some of that so as to not distract us too much to start with here. Focus our attention on the first thing. So the definition of the cross product of two vectors is this. You notice the formula, it's got like, in the first component, it's got the second and the third. In the second component, it's got the first and the third. In the third component, it's got the first and second. It's always missing whichever it is. One's missing from here, two's missing from here, three's missing from here. Now, it turns out that that definition has some really cool consequences. For one thing, it makes A cross B equal to minus B cross A. So it's not commutative, it's what's called anti-commutative or skew. So it's minus itself. And notice what that would say. What happens when you take the cross product of a vector with itself? Like A cross A would be minus A cross A, but what's that mean? That means any vector cross product with itself is 0, right? In contrast, any vector dot product with itself was what? Was the length of the vector squared, right? And in fact, you can prove that if you take A cross B and you take the dot product with either one of the vectors, let's look at A, then what you'll get is 0. What's that mean? That means that geometrically, this vector A cross B is perpendicular to A. And in fact, you can also prove the same about B. A cross B dot B is equal to 0. So the cross product, first and foremost, is a vector, right? In contrast, the dot product was a number, a scalar, right? But the cross product is a vector which is apparently perpendicular to both of the given vectors, right? It turns out that you can describe it geometrically using the right-hand rule. If you take your right hand and you point your, so like here, if this is A and this is B, so I point my right hand in the direction of A and cross my fingers into the direction of B, the direction my thumb points at, that's A cross B. So the way I would illustrate that here is that there's a vector pointing out of the page, A cross B. On the other hand, if the situation is that A is this way and B is this way, right? When I point my fingers in my right hand direction in the fingers in the direction of A like this, I can't cross into B. I have to turn my hand over. See that? I have to turn my hand over in order to take my fingers from A and cross them into B. I'm forced for my thumb to point down into the page. So we draw an X. We're imagining like an arrow. If I can draw a picture. So here's the sort of silly picture of what's the word? Oh, an arrow, right? I'm an idiot. I can't draw it. Curses. Well, like that, an arrow. These are the tail feathers, if you will, and this is the tip of the arrow coming out at you. I have more pictures in the notes, which may or may not be better. I don't know, but you can see. So and I explain in the notes in some depth, like if you're looking for a way to take two vectors and combine them to give a third vector, which is perpendicular, you're driven to this formula up to a scale factor. And we'll see that scale factor is actually fixed by the geometry. Well, I'll just tell you now that the significance of the magnitude of AB, the length of AB, is in fact equal to AB sine theta. And if you were to look at like the little parallelogram with side lengths, you know, like A and B, and angle theta between it, you can see that this magnitude, the magnitude is actually the area of the parallelogram with sides A and B. So that's the significance of the magnitude. Like that area is the magnitude of the cross product. And the direction is given by the right-hand rule. Okay, we'll come back to that. I want to talk a little bit about, you know, what this cross product is before I just blather on about how to calculate it. But let me now blather on about how to calculate it. Here, I'll call this page 9, so I don't forget to include it. Now, another popular formula for the cross product is this mnemonic. So this is the determinant. I think you guys have seen determinant in your previous like matrix course. That's another way to remember this formula. Or you can look at it in terms of index notation. This is like a slick formula for the cross product. I use this to make proofs. There's also a slick formula for the dot product. A dot B is the sum over j equals 1 to n of aj bj. And there's other like sneaky stuff, like the dot product of x hat and x hat I and x hat j is Kronecker delta. I guess I should write that down. Kronecker delta. This is the Kronecker delta. Kronecker delta is a combinatorial convenience. It's 1 when I and j are equal, it's 0 when they're not. And then there's also this guy. This guy here is what's called the Levi-Civita symbol, or sometimes the completely anti-symmetric symbol. And it encodes the formula up there, basically. The way this works is that epsilon 1, 2, 3, 2, 3, 1, 3, 1, 2 are 1, whereas 3, 2, 1, 2, 1, 3, and 1, 3, 2 are minus 1. And so that generates this plus, 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 and this minus, minus, minus in that formula. And trust me, when you're doing something about the cross product properties, like from an abstract perspective, this is like way, way better for proofs. And I show you that in my notes, and I think there's like one bonus homework problem on that. That's not something that would, you know, typically be the, let's say, meat and potatoes of the test, but it is nevertheless interesting to me, at least, if not to anyone else. But so key idea is that the cross product of two vectors creates a new vector which is perpendicular to both of the given vectors. The cross product has really nice algebraic properties. It's almost like the dot product. It's just, number one, it's a vector, and number two, it's this skew commutative. But you know, there's you can draw this. If I have x hat, if I have y hat, and I have z hat, you can make like a little circle. And this circle helps me to remember that, like x hat cross y hat is z hat, y hat cross z hat is x hat, z hat cross x hat is y hat. And so you could use that to do some calculations. I have explicit examples in the notes. I'll let you look at those. I don't want to. I guess we could do. It probably would be good to do at least one here. Let me do one. All right. I'll do it on the next page. Actually, the next page, because that brings us to 10. All right. So here's an example. By the way, I should mention, if you need to see much more examples, I mean many, many more examples, my YouTube channel has, you know, complete video lists of Calculus 3 that I taught at Liberty. It's probably going to be too much for you to look at. I mean, it met 5 days a week, and I have something like, oh goodness, I don't even, there's a lot there. But if you thirst for additional examples, you ask me, I'll try to send you a link. I know you guys might have some trouble looking at those, but it might be worth it if you get stuck on a particular topic. because I'm going to try to keep these somewhat brief, believe it or not. Okay, so example, let's let a equal to 1, 1, 2, and I'll let b equal to 0, minus 1, 6. So how do we calculate a cross b? Well, I will use the determinant trick, because I will admit, I think I tend to do better with that when I actually do it this way. I don't know. Listen, calculating the cross product of two vectors, it is a dangerous game. It involves a lot of arithmetic steps, and you gotta check your answer. So first of all, x hat. All right, then the expansion of the determinant. We kind of like expand on this part right here, right? So it's going to give me 1 times 6 minus 2 times minus 1, right? And then the way the determinant works, the next one is minus y hat, right? And then that involves everything that's not in there. It involves these numbers. So I have 1 times 6 minus 2 times 0. All right, then plus z hat times, and it's everything that's not in that one. See if I can find yet another. I'll use the brown. So it's like these guys. Okay, so 1 times minus 1 minus 1 times 0. Those are the ones that go into the z hat. So what do we got? We have x hat times 6 minus a minus 2, so that's 8, minus y hat, and this is 6 times 6, plus, well, actually that's a minus 1, so minus z hat. Now, I usually like to write that answer. I rewrite it as this. That's 8 minus 6 minus 1. Okay, now there's a lot of steps there, right? So did we do it right? Let's check. How do we check? Well, the easiest way to check is, let's see, is a dot 8 minus 6 minus 1 equal to 0? Question mark, right? In other words, we're looking at 1, 1, 2, dot with 8 minus 6 minus 1. What's that? Well, that's 1 times 8 plus 1 times minus 6 plus 2 times minus 1. So that's what? That's 8 minus 6 minus 2, also known as 0. Woohoo! So this is at least perpendicular to A, and you can just kind of eyeball it for B. If I do 0 times 8, I get minus 1 times minus 6, which is plus 6, and then minus 6. So when I take, you can likewise check that B dot 8 minus 6 minus 1 is equal to 0. Now that, I guess technically speaking, that doesn't absolutely prove you're right, but you'd have to be so unlucky. You have to be so unlucky to still somehow get both of those to work out to 0, and yet to be wrong. In practice, usually if you just check one of them and see that the dot product is 0, it's probably going to be okay. But you should check at least one of them, because this cross product calculation, it's like a pain, right? And you need to check on it. I see so many students that needlessly waste points because they don't check their cross products, this is unfortunate. All right, I'll shut up about that. Now, so just to rehash, what's the meaning of the magnitude of the cross product? No, I won't try to squeeze it onto this page here. I'm going to do the next one, 11. So the geometric significance So as I was saying, if we have a vector A like this, right, and we have vector B like that, then the angle between them is theta. If you draw B again up here like that, right, and if you draw A again over here like that, that makes a parallelogram. And in fact, you can do the geometry here, right? So like this has length A. So if you look at this right here, this would be what? This is A sine theta, right? And what's the length of the base? So that's the height of the parallelogram is A sine theta. The base of the parallelogram is just length B, right? So the area of this parallelogram would be A B sine theta. So that's the well, this I suppose this is not obvious, right? What I'm about to write, it's not entirely obvious. Well, let me back up a second. It is far from obvious that A cross B is equal to AB sine theta n hat. But it is true. I prove it in the notes. It takes me about 2 pages, I think. So what I'm saying is that it's not obvious that that's equal to that when we have defined it not by that, but we've defined it how? We've defined it by this formula back here, right? So why is that equal to that? That's not at all obvious. So if you look at my notes, I'll tell you, page, eventually I'll find it. Come on. Oh, so much jibber jabber. All right, come on. Come on. Where'd you go? Well, I do have more examples in the notes, but I would say it's the proof of that is mostly on like pages 33, 34, 35, somewhere in there, give or take. But it's not entirely obvious why that should be true, but it is. And it also actually retroactively explains why the formula is what it is, because it's chosen to be what it is because that makes the magnitude to be the area of that parallelogram. I should mention some deeper properties, if you will. These are not particularly easy to show, but it's kind of fun to know about them. One is that A cross B cross C does not make sense. You have to put parentheses. The cross product is not associative, but this much is true. A cross B cross C is equal to A dot C times the B vector. I don't expect you to know these, but it's nice to know about them, okay? A dot B. So what do I expect you to do? I expect you to be able to calculate cross products and do problems like the homework, all right? So this is sometimes called the back cab identity. And then there's also something called the Jacobi identity, which is kind of neat. I'll just take a second to write it down and talk about it. So while the cross product is not associative, its departure from associativity is actually measured by this so-called Jacobi identity. So, but I've not found many Calc 3 problems which really require use of this. They're out there, they exist, but they're kind of hard to find. This is the Jacobi identity. It's the first example. The cross product is actually an example of what's called a Lie algebra, which is something my brother more or less studied in graduate school. Well, his PhD topic is kind of an extension of that. More important, now this we actually do need for applications often, and that's that A dot B cross C is equal to B dot C cross A, which is equal to C dot A cross B. This is what I would call the cyclicity of the cross product. And the geometric significance, and these are all, by the way, what are called, these are all triple products. And the triple product gives volume. In particular, the volume subtended by a parallel pipette with sides A, B, C is equal to the absolute value of the A dot B cross C. It can be shown that that's the same as the absolute value of the determinant of, and you just put A in the top slot, B in the second slot, C in the third slot. Or you can put them as columns, because the determinant doesn't care if you put them as rows or columns. But you just stack the vectors, take the determinant, that gives you the volume. Well, plus or minus. Whether or not it's a plus or minus depends on whether these are what's called a right-handed triple or a left-handed triple. Let me just talk about that for just a second here. So just draw a picture. So you can imagine a plane. In fact, that's what we're about to start talking about in the next lecture, so it's good to getting into it. But in this plane, if you had like vector A was like this, right, and vector B was like that in this plane, right? And then we think about the set A, B, and then we add a third vector, let's say C. The question is that a right-handed triple or not? Make sure you can see it. So here's the deal. If A cross B puts you like above the plane like that, C doesn't have to be exactly in the direction of A cross B, but as long as it's on the same side as long as it's on the same side of the plane as A cross B, that makes this a right-handed triple. And if ABC is a right-handed triple, then you actually don't need absolute value here. A dot B cross C will literally give you the volume of the, I'll foolishly attempt to draw it, A, B, C. This guy, the volume of this guy. This is supposed to be like, parallel. So there's like another B back here, there's another C right there, there's another A right there, and so forth. So these legs would all be C. C, 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 A, B, 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 B. That would make it right-handed. On the other hand, if you had, let's say, D that was like this, I'll draw a dotted to indicate it's below, then the set A, B, D you could call it left-handed, and that means that D is below the side of the plane where A cross B points. And in that case, if you were to calculate the determinant of ABD, you'd get minus the volume. So that's the significance. One of the significances of the volume of the determinant actually is that it has to do with volume. I mean, determinant is volume, volume is determinant. It's just not a wrong slogan. I think that's the other thing I have to say about the cross product is and dot product. So cross product and dot product can both be used to judge whether two vectors are parallel. If two vectors are parallel, the dot product is like as big as it can be. The cross product is 0 if two vectors are parallel. In contrast, right? I should write this down. Sorry guys, I should write this down. So, parallel. So A parallel to B versus perpendicular. So let's compare and contrast these. So here A cross B equals to 0. A dot B is equal to AB. Because if they're parallel, the angle between them is 0, so cosine of theta is just 1. All right? Now, if they're perpendicular, A cross B is equal to A, B, and a unit vector. Because the angle between them is 90 degrees, so sine of 90 is 1, so AB. So it's basically as big in magnitude as it can possibly be. But on the other hand, A dot B is equal to 0. So the bigger the dot product is, the more parallel they are. The dot product, on the other hand, being 0 means they're perpendicular. If the dot product is equal to minus AB, that means that they're pointing in opposite directions. They'd still be what's called collinear, but they'd be anti-parallel if they were like opposite directions. And vice versa. For the cross product, it's 0. That means that they're parallel. Whereas if the cross product is as big as it can be, that means that they're perpendicular. Bigger cross product, more perpendicular. Smaller cross product, less perpendicular. And vice versa for the dot product. So I think these are important concepts to be aware of, because we use both the dot product and the cross product to understand the geometry of vectors. So, okay, with that, next time we'll talk about lines and planes and such. And thank you.